Hello, everyone. My name is Keith Nicholas. I'm an applications engineer with TI's Precision ADC product line. And today we're just presenting a short video on how to create custom digital filters for one of our latest wideband Delta Sigma converters, the ADS127L21, using MATLAB and ADS127L21 EVM GUI as a combo set to actually download the coefficients and then see the filter response and look at a few measurements. So real quick, on this presentation, which you can find later and download for offline viewing, the L21, the agenda right now, we're just going to focus on this first section, which is really the nuts and bolts of how to go through the process of using the MATLAB Filter Designer tool to create a custom filter and then download it to the ADS127L21. These other two sections are really just supplemental backup material that you can look at later to better understand how all of this is implemented inside of the actual ADC itself. So first thing I want to emphasize here, this presentation is based on the free MATLAB online only version. So this is a cloud-based tool that MATLAB provides. The basic version is free. You sign up for a MATLAB account and then you'll have access to this tool. And within that tool, once you start the MATLAB Basic, there's this filter designer GUI that we'll be using extensively in these examples. There's absolutely no writing of scripts required, so you don't have to learn how to program in MATLAB if you're not already familiar with it. And it's a very simple graphical interface. You simply enter the high-level design parameters that you want and click Design Filter. The tool will generate a text-readable file, which is what I'm showing here in the middle. Then from here, this file can easily be opened up inside of our EVM GUI software for the L21 and evaluated on the actual hardware platform. Just a real quick background, inside of the ADS127L21, the configurable coefficient block diagram, the filter that we're going to be programming to is this programmable FIR3 filter stage that consists of 128 coefficients. And then the programmable IIR stage is another optional one that can also be programmed. This is a 4-section, 8th order, fully programmable IIR stage that you have access to as well. But real quick, what the internal filter signal chain inside of the ADS127L21 looks like. There's a first stage Sync5 filter. This is the first stage of filtering straight from the modulator data output. And this is where most of the decimation takes place when you set the OSR settings and the registers of the ADS127L21. You basically are adjusting this from ×4 to ×512. So effectively, whatever the data rate here is on the input, you divide by this level here, and then that's what you get on the output. Followed by this, there's another filter stage. This is an FIR filter. These are fixed coefficients. These are pre-programmed inside of the L21 device. And this is a sync compensation filter to flatten out the response in the band of interest that we're going for. Followed by that is another half band FIR filter for further decimation and to keep the passband that we're interested in very flat. And then finally, we get into the programmable filter stages that we're going to be talking about here in this presentation. This FIR3 stage has up to 128 coefficients that you can program into it. And then there's also an IIR stage that you can program. So again, just as a quick overview, this is the tool that we prefer to directly use to design IIR and FIR filters. There are other available tools that you can use as well. This is the one we use at TI though, and it's the one that I'm personally familiar with. So that's what we're doing the examples here in this video. And then also, again, I'll just restate the version that we're using is the free basic online version. So anybody should be able to get access to this tool by signing up for a free account at MathWorks MATLAB website. You can also use, of course, the download version. That's a version that you have to pay for. But if you do decide to go that route, the one extra plugin that you'll need that's a separate package is a signal processing toolbox. And that is needed because that includes the filter design tool, which is this graphical user interface here. Just as a high level, the Filter Designer is a graphical based design tool that enables the creation of multiple filter types. You can see here you got the options of a low pass, a high pass, a band stop, and then here you can choose between an IIR filter or an FIR filter, and then there's multiple filter profiles that you can select depending on which one of these types of filters that you want the design to. All right, now we're going to show an example of how to actually go through the process to design a filter. In this example, we are going to design a 20 kilohertz low pass filter for a 256 kilosamples per second data rate using the FIR filter capability inside of the ADS127L21. Just as an overview of what the end result is going to look like, as I mentioned, it's going to be a 20 kilohertz low pass filter, target data rate of 256 kilosamples a second. We need to make sure this filter that we design using MATLAB Filter Designer tool will fit within the 128 coefficient limit. And we're going to target a stop band attenuation with more than 100 dB of attenuation, as shown here on this example. So with that, I'm just going to jump out of the presentation and then I'll kind of walk through the actual step of using the tools. Here I'm in my Chrome browser. I have signed into MATLAB, and this is the home screen that you'll get under your own account. All of your files that you generate within the MATLAB tool get saved to a cloud drive that MATLAB maintains for you. And then you have the option to download, as I'll discuss here later on. But to start, we'll go ahead and start the online MATLAB tool that we'll be using to design with. And I'll note as this is loading that we're going to completely use the Filter Designer tool, which is a complete graphical interface. There is no requirements to write any code in this example. So the only thing I got to type in here at the command window is the tool itself. I will note that MATLAB is case sensitive, so make sure it's all lowercase with the exception of the D. And we'll hit enter, and then we'll launch the actual Filter Designer tool. So real quick, as you can see, this tool gives you a lot of options. We can design a low pass, high pass, band stop filter. We can design a filter for IIR, which the L21 device also supports. But for this example, we're going to design an FIR filter. And then we have a bunch of filter profiles that we can choose from. For now, we're going to stick with the default equal ripple for the FIR. But if we've been designing an IIR, we would have also had an option of a few different ones as well, including Butterworth and Chebyshev. But for now, again, we want to do this 20 kilohertz FIR filter, so the low pass and FIR are already set for you. Now we do have an option. We can specify the order, and we have 128 coefficients, so the filter order is one less than that. So we could specify 127 here for the filter order, and whatever it designs will fit into the L21 register space. But I find that it's easier to do a minimum order where it will calculate the number of coefficients that you need. And then I like to do an iterative process to get to the exact design that I'm after that will fit inside of the ADC. It gives you a few more options over here where you can set the pass band ripple as well as the minimum stop band attenuation. If you specify the order, you don't get those options here. So that's, again, why I like to use the minimum order. And that's the example we'll use here. I had mentioned in the slide deck that we want a 256 kilosample rate. If you look in the L21 data sheet, you'll see that after this filter stage inside of the device, there is a decimation by 2. So the output data rate is 256. So this filter is actually running internal to the ADC at twice that rate because of the decimation of 2. So in order to design this for 256 output, we need to design the filter at actually 2 times that, or 512 kilosamples a second. Now for the filter, we want a 20 kilohertz bandwidth, so we'll enter it in hertz here, 20,000. And just as an example, I will enter a stop band at 30,000. For the pass band, we really don't want much ripple, so I'm going to enter a 0.01 dB. And before I'd mentioned the goal was more than 100 dB of attenuation, so I'll just put in a little higher at 105. Now that's it. I've entered all of the data that I need to enter, and I'm ready to click the design filter. So we'll click it. It usually only takes a few seconds. And now you can see the filter that MATLAB has designed for us. But if we look over here, the filter order is 250, which is almost double the actual register space that we can implement inside the L21. So this filter is clearly too aggressive for what we can build and load into the L21. So we need to do one of two things. We either need to widen the transition band. In other words, the difference between the f-stop and the f-pass frequency needs to be larger, or we need to reduce the amount of attenuation or increase the amount of ripple in the pass band. In this case, I'm going to just widen the transition band to 40. And then once I re-enter that number, I'm going to click Design Filter and we'll be able to redesign it. So now we have the plotted filter response. It still looks very good. And the order is 125. We can go up to 127, which is 128 coefficients. So this filter is good. We can actually load this into the L21 filter. So at this point, we'll call this a good design. And now we need to save these coefficients off that were generated internal to this filter designer tool to actually generate this magnitude plot. So the way we do that, we want to save those coefficients that we need. We'll go up here to click on File and then click on Export. And at that point, we'll get this export window that opens up. And what we'll want to do is go to the Export To and select Coefficient File ASCII. This is just a text file with the actual coefficients in it. Now, these coefficients are double floating point numbers, and we'll save them in this case as a decimal. So what it means is it'll just be an ASCII file with the actual floating point decimal values in it. We could also save it as a hexadecimal, which is just the binary form of the IEEE 754 standard floating point numbers. But the EVM GUI software will accept either format, so we'll just stick with decimal for now. So at this point, we would click on Export. When we do, if we go over here, it will save it here. And you can see that I've already saved it to my workspace, and I saved the file right here as this one. So we can inspect what MATLAB generated. Just double click on this file and it will open it up over here in the viewing window. And now you can see the actual text file that MATLAB created. These percent signs are comments, basically, that just describe what we just generated. It's an FIR. It's an actual total length of 126 coefficients. It's in decimal format, and you can see right here what it actually printed out. And if we were to scroll all the way down, we'd see all 126 coefficients. So once this has been done, our file is now saved in a format that the L21 GUI software can read, but we need to save it to our workstation. This is still in the MATLAB cloud. It's a personal cloud space that MATLAB generates under your account name. So it's saved there. It's a simple matter. Just go over here and right click on the file and click on download, and then we'll download it to your download directory. And from there, you can open it from the EVM. So I just started up the EVM GUI. This is the default page you get when you first start it. If we go over here to Pages, we'll click on the digital filter configuration file. And you can see right now, all of the coefficients for the FIR filter and the IIR filter are the default values that are preloaded inside of the L21 device on power up or reset. So we need to load these in. So what we're going to do here is go here to the FIR3 coefficient file, and I am going to then navigate to where I have these saved on my workstation here. And this is where I had saved it to previously. This low pass FIR filter is this one right here, decimal format. I am going to click on it and then click Open. And as soon as I clicked on it, the EVM GUI read that file in, and then it converted those numbers to the fixed point 32-bit values that are required to store into the L21 device itself. And that's what we're displaying here. Not the floating point decimal version, but a hex code 32-bit fixed point version. And you can scroll through and you can observe what these are and see what they are. So these are now read into the device. So now I'm going to click on filter response so we can get a calculated plotted response of what the filter will look like. Again, I had designed it for 256 kilosamples, so I'm going to increase the default oversampling ratio from 32 to 64, which will divide the output data rate to 256. And the plot that we're getting is the default built-in FIR filter that is inside of the L21. But we want to see what our response looks like. So we can see this one at 256 kilosamples a second has a flat response to a little over 100 kilohertz, and then is fully rolled off before the Nyquist of 1/2 of the data rater 28 kilosamples a second. So what we'll do is up here under filter selection for FIR, it's under default coefficients. We're going to select user defined, which are the ones we just loaded into memory. And now you can see the default is from 20 to 40. And now we're good to go. So we can actually run actual tests on our EVM. So as an example here, I do not have anything connected for a signal source on the EVM, but what we can do is configure it to just take a bunch of samples and run a histogram to see what the total noise of the EVM is. So if I hit capture here, we can see we have 3.8 microvolts of RMS of noise with the 20 kilohertz filter that we just created. Just as an example, this is roughly a 20 kilohertz bandwidth filter. If I go back to the built-in filter coefficients, it's closer to 100 kilohertz. So we would naturally assume that our noise should be higher now. So if we go back to the histogram analysis with the exact same settings and hit capture again, we'll see it went from 3.8 to 8.6 microvolts RMS. So we can tell that it is actually using the filter that we ran. And of course, if we actually did like a frequency sweep with a signal generator, looking at it in spectrum analysis or the Fourier transform, we could see the effects of this filter then on our input signal. Anyway, I hope you enjoyed the video. That concludes it. Please, if you have questions, you can submit questions on our E2E forum regarding the ADS 127L21. Thank you.